This is the first section of Chapter 8, Decision Analysis, and this section is all about decision trees. So first of all, what is a decision tree? Well, a decision tree is like a tree diagram. It looks like a tree diagram. There are one or two differences, but the whole purpose of a decision tree is it helps us to make the best decisions based on what we call the expected payoff. Now, you would have come across payoffs before in a previous chapter on game theory when we looked at a payoff matrix. So here's an example of a decision tree. It looks something like this. All these different boxes and triangles and circles all mean something different. So if we have a box like this, it's called a decision node. A decision node. And basically, as the name suggests, the decision node appears where we have a decision to make. And you can see these lines here. These are going to represent the two different decisions I can make at this point. Now the circle here, this is called a chance node. So I'll just put that on. So if you see a circle, it's called a chance node, if I spell it correctly, chance node. And when we're drawing a decision tree, inside of the chance node, we write what's called the expected monetary value, or EMV. Now these triangles that are at the end here are called end or payoff nodes. So it's either called an end node or a payoff node. Now, based on this EMV value here, may decide whether I'm going to play this option or not. And if I'm going to play an option, if I'm going to take an option, then we'll write P on that branch. If I'm not going to play an option, I'll put like that little squiggly line, tilde, and this means not to play. So we'll just write that down. So here, not play, we're not going to take that option. And here, this means that we're going to play and take that option. And that all depends on whether it's worth it or not. Is our expected monetary value going to give us some sort of incentive to take this decision? Are we going to be gaining time, money, or something like that by taking this option? It may be that this is not a good option to take, and we may not take this option. We may decide not to play. Now, if we decide that there's a branch that isn't an optimal strategy, so we're not going to play it, it's not an optimal strategy, then you'll put two bars across a line like that, and that's because it is a non-optimal strategy. And that will change depending on what the question is all about and the expected monetary value and so on. Okay, let's have a go at some examples. Example 1. Carol plans to travel from Cannock to Derby by car. One option is to take the A460 to Uttoxeter and then take the A50. This is a distance of 38 miles and will take around 1 hour 20 minutes. The second option is to set off on the A5 to the M6 toll road, then continue on the A38. This is a distance of 36 miles and will take around 55 minutes. A final option is to combine the routes by taking the A60 to Rugely, I think that's how you pronounce it, and then the A515, and then take the A38 to Alrilwas, I think that is. This is a distance of 34 miles and will take around 1 hour and 5 minutes. Part A, we want to use a decision tree to choose the best option for Carol based purely on, first of all, the distance to travel, and then secondly, the time needed to complete the journey. Okay, so our first decision tree is going to be based on distance. Now, any decision tree always starts with a decision mode. So that rectangle box, that's the first thing that we draw. Now, there are actually three options or decisions. So you think I'd have three lines there. So the first option starts here and it's described there. And we've got the second option, and then we've got this third and final option here. But two of the options start on the same road, the A406, that's option 1, and option 3, the third one, both start with the A406. So I don't need three separate lines. I can basically start off one option up here, options 1 and 3, which start with the A460. Did I say 406? I meant 460. And then the second option I'll draw with another line down here, and that's the second route that starts off on the A5 over here. Okay, now what I'm going to do, I'm actually going to continue this second option here, the one that's the A5 route, because it you know, there's not going to be any other decisions to make. I'll just end up at my end node here, or my payoff node, and in this example the payoff is going to be distance, and this one, the A5, the second option, so it's the A5, then the M6, and then the A38. So let's just put those 3 roads on. So let's do it in a different colour. So you've got A5, and then from the A5 we're going straight to the M6 toll road. Toll just means we're going to have to pay at some point to continue using that road, and then it's the A38. Now the payoff for taking this route is, in terms of distance, because we're looking at the distance, is 36 miles. So we write the payoff next to the payoff mode, so it's going to be 36. Now let's go back to the other 2 options. So we've got the A460, and what we've got is we've got a decision to make once we've taken that first road, and that's going to be options 1 and 3. So let's complete that by moving on. So option 1 is take the 460 and then take the A50. Right, so that's one decision we can make up here. So this road here is going to be the A50. Now what's the payoff for taking that route? That's option number 1, A460, then the A50. That's a distance, a payoff of 38. So I'll write 38 here. And then option number 3 starts on the same 460, and then it takes the A515 and the A38. Now I don't need to show that on 2 branches. I can just combine the 2 roads onto one. So the A515 followed by the A38 here, and we'll work out the payoff for that one. So here's my payoff node, which I'll do in black. Whoops, don't want to take lines out, so here we go, like that. There's my payoff node or end node, and if I take that route, so that is route number 3, in terms of a distance, that's 34 miles. So I write 34 here. So when we draw one of these decision trees, the payoff is written next to, on the right hand side of the payoff end node. Okay, so what we need to do is to choose the best option. Now based on distance, the best option is going to be the one with the lowest distance, and that's going to be this route here, which I'll highlight in yellow, and we'll just write that down. So best route in terms of distance is the 460, the A515, A38, and that's a payoff of 34. Now we'll move on to looking at the best option in terms of time now. So it's going to be a similar payoff matrix, but rather than have distances on there, we're going to have times. Okay, so I've just copied out the same diagram again, because this is all the same. All we're changing now is time, and the payoffs now are going to be times rather than distances. Okay, so remember the top branch here, that is option number 1, A460 followed by the A50, and this payoff is 1 hour and 20 minutes. Let's write it in minutes. So that will be 80 minutes for taking that route. The second option, remember, is this bottom branch down here, and that will take around 55 minutes. So the bottom branch has a payoff of 55 minutes. Now with these payoff matrices, we don't need to put the sorry, not payoff matrices, with these decision trees, we don't need to write the units on. It's enough just to write numbers down because we're comparing like with like. And then this branch here, this is the third option, and that's 1 hour 5 minutes, so that's going to be 65 minutes. So I write 65. So I can see from this that in terms of time, it is the lower branch down here which is the best, which has the lowest value, the best payoff in terms of this problem. So the best route in terms of time is going to be this lower route down here. So that's going to be the A5 followed by the M5 toll, then followed by the A38. So that's not the same route as the first one. So I guess it all depends on what Carol's priority is. Is it getting there as quick as possible in the shortest time, or is it trying to save petrol by taking the shortest distance? Okay, the cost of driving is estimated at 40 pence per mile. There is an additional cost of £10 for using the M6 toll road. Comment on the best option overall. So what I'm going to be using in part B is the same decision tree, but this time it's going to be based on cost, taking into account the toll road costs and the cost of driving per mile. Same decision tree as before. Okay, now I need to work out these costs. They're going to be based on distances or whether the toll road has been used. So if we look at the first option at the top, there's no toll road here. Doesn't use that motorway, so it's just going to be the distance 38 times by the cost per mile, which is 40 pence, so times by 0.4, and that gives me a value of 15.2, £15.20. So I'm going to write 15.2. Remember, we don't need to write down the units, so just 15.2 for that one. If I take this route here again, there's no toll road, so to work out the cost of that route, it will be 34 times by 0.4, and that gives me a payoff, a value of 13.6, £13.60, so 13.6 here. And then for the lower route down here, well, I've got the 36 miles times by the 40 pence, but because I'm taking this M6 toll road here, there's an extra £10 charge which needs to be added on. So let's work out what that payoff is, and it comes to a total of 24.4, £24.40. So that's a payoff of 24.4. Now what we can do is comment on the best overall option, looking at the answers that we got before, which were the best options for distance and time. So let's put all of that information together and see what we come up with. So the best option in terms of distance is the A460, the A515. So this is the best option for distance, so best for distance. The best in terms of time, that's the toll road route, so this is best for time. And the best option in terms of cost is this one here, the middle option here, A460, A515, A38. So this is the best for distance and for cost. So my advice to Carol would be to take this middle option here and take this route, because in terms of distance and cost, it's the best route. However, we've got this toll road, that's the best for time, but is it worth it? Is it worth paying, another £10 just to save a few minutes on journey time? And I think actually Carol would only save 10 minutes taking this route, and is it worth paying £10 to save 10 minutes? That's £1 a minute. Example 2. James is trying to decide whether or not to play a game using 2 fair tetrahedral dice. The sides of the dice are numbered 1 to 4. If he scores a total of 6 or more, then he wins £4. Otherwise, he loses £2. Part A, draw a decision tree to model James's possible decisions and outcomes. Okay, so with a decision tree, the first thing that we have is a decision node here. Now, he's got this game, he's deciding whether or not to play. So the two options are he plays or he doesn't play. So P for play and tilde P for not play. Now, if you don't play, you don't win, you don't lose. So the expected payoff is 0. So we always write down the expected payoff, even if it's 0. Now, when he does play, there are options in terms of whether he wins or loses. So this is where we put a chance node. So that's going to be a circle. So remember, a circle is a chance node. And this is going to have our probabilities of whether he wins or whether he loses, and how much he wins and how much he loses. And from that, we can decide what we're going to do. Are we going to play or not play? And in here, we'll put the expected monetary value, the EMV, and that's going to help us decide whether to play or not play. If we're going to play and lose money, we might decide that our best option is to not play. So he's rolling these two fair tetrahedral dice. They're numbered 1 to 4. If he scores 6 or more, then he wins. So I'll just put, if his score is greater than or equal to 6, he's going to win. His expected payoff is £4. And then if he gets, if he gets less than 6, he's going to lose £2. We write that as -2. Now I need to work out what these probabilities are. So let me just do a quick sample space diagram and write down the totals of rolling these two tetrahedral dice. And like magic, there it is. So how many options have I got of getting 6 or more? 1, 2, 3, 4, 5, 6. So that is a probability of greater than or equal to 6. I'm not sure why I wrote it like that. Greater than or equal to 6. That is 6 out of the 16 options. So I can simplify that to 3/8. So the probability of me winning is 3/8. So that means the probability of me losing, where it's less than 6, is going to be 5/8. Okay, so this is where I can now work out the expected monetary value. And the way that we do that is we are going to multiply the probability by the expected payoff and find the total of those. So if I do that, that will be 3/8 times by 4, and then it'll be minus 5/8 times by 2, because the minus is the with the loss there. So it might make more sense actually to write the value first. So 4 times by 3/8 minus 2 times by 5/8. And if you do further statistics 1, or you know anything about finding the expected value of a function, you'll see it's exactly the same type of calculation, where you do the outcome times by the probability of that outcome. So what will this give me? 4 times 3/8, so that'll be 12/8 minus 10/8, which gives me 2/8, which gives me a quarter. So that means that the expected monetary value is a quarter, or we can write that as 0.25. And that's going to go in here. So let's put that in, 0.25. So we can move on to part B. It says determine whether or not James should play the game and state his EMV. Well, we've done that. His EMV is equal to 0.25. It's positive. So maybe James should play the game because his expected monetary value is 0.25. We're expecting to win more times than lose because we've got a positive value here. So I'll just put that down. James should play since his EMV is positive. So this will be his optimal strategy. And remember, if we have a non-optimal strategy, 2 bars like that to say, well, we're not going to take this option of not playing. Playing is his best optimal strategy in this case. Example 3. Jess plays £2 to play a game. She rolls 2 dice, and if they both show the same score, she wins £5. Otherwise, she loses. If she loses, she can pay a further £1 to roll a 3rd dice. If the score on a 3rd dice matches the score on either of the first 2 dice, she wins £6. Otherwise, she loses. Part A, draw a decision tree to model decisions and possible outcomes. Okay, so we start with our decision node here. So Jess can either decide to play or not play. We'll look at the play options in a moment. So play here, not to play down here, and we can fill in the expected payoff here. That's going to be 0. Right, so it starts by rolling the 2 dice, and she can either get the same score or not get the same score. So we'll do that here at this chance node. So it's either same score or not the same score, so just put different here. And we'll put the probabilities on if I've got enough space, and I've got like a sample space diagram here. So the same score is going to be 6 out of 36, so that's, you've got 1/6 chance of that happening. So we'll write down 1/6. So obviously it's going to be 5/6 if they're different. Now if it's the same score, it says she wins £3, but she's already paid £2 to play the game. So overall, she only wins £3. So we don't put -2, we don't put 5. It's going to be a score of 3. That's basically how much money you've made. You've used 2, you get 5. Basically, you've won £3. But at this point, it doesn't end, because you see, if she loses, and this will be losing down here, she can pay another £1 and play again. So this is not going to be an end node, a payoff node here. So we're going to get rid of that. Still the same probability. At this point, she's now got a decision to make. Does she pay the £1 and play again, or not play? So we'll put that on. She can pay £1 and play again, or she can not play. So down here will be the option not to play. Okay, she's not won. Fair enough. We'll just stop there. And at this point here, she just would have lost the £2 that she's paid to play the game. So -2. Now let's see what her options are, her chances are when she gets to this point. So it says she's paid another £1 to play and get to this point here, and then she rolls a 3rd dice. If the score on a 3rd dice matches the score on either of the first 2 dice, she wins £6, otherwise she loses. Okay, so let's see how we can work out this probability here. If we've got to this point, then it means that the dice that we threw before, the numbers didn't match. That means we've got 2 different numbers on our dice. So we've got 2 out of the 6 possible numbers on the dice. So if I throw a 3rd one, I've got a 2 out of 6 chance that that number is going to be one of the 2 numbers I got. And 2 out of 6 is going to be 1/3. So the probability that that's going to happen is going to be 1/3. And then obviously the probability that the 3rd dice doesn't match is going to be 2/3. I've got one of the other 4 out of the 6 numbers on the dice. Okay, let's now work out the expected payoffs. So if I've got to this point, I've already paid £2 to play the first game. I've lost, and then I pay another £1 to play again, and then I win £6. So that makes 3. So the expected payoff would be £3. Let's put a 3 there. If I get to this point down here, I've paid the original £2 to play once, I've paid another £1 to play again, and I've lost it. So I'll put down here -3. Okay, so now I can work out the EMV, expected monetary value, for this box here. I'll just do like a highlighted line down here to show my working. And that working is going to be 3 times a third minus 3 times by 2/3. We work that out, we get -1. So I'll put my expected monetary value here of -1. So now I want to work out this EMV here, so I need a value in this box, decision box, and that comes from the EMV of playing here, and so that's going to be -1. So you're always like almost working backwards, so that -1 will go into my decision box. That will allow me now to work out the EMV here. So the calculation for that is going to be 3 times a 6 minus 1 times 5/6, and that gives us a value of -1/3, which we could either write as 0.33 recurring. So let me put it as a decimal. So I'll put -0.33 just in there. So now we can move on to part B and find the best strategy for Jess as indicated by the decision tree. Okay. So if she hasn't started to play, then she shouldn't play because her EMV is negative. So I'm going to strike this out here. So if she's at this point, then she shouldn't play. If, however, Jess has already played once and she's at this point and deciding whether she should play or not, well, her best option is actually to play again because her EMV here is -1, but even though it's negative, it's going to be higher than the payoff that she gets here. So I'm going to strike out this bottom branch and then write down what she should do if she's at this point here. So if Jess has already played once, she should pay the £1 and play again. Example 4. Jack has time for one revision session before he takes an exam in mechanics and statistics. He will devote this time to either mechanics or statistics. These are worth 50 marks each. Jack estimates that if the mechanics questions go in his favour, then he would expect to achieve 45 marks. But if they don't, then this reduces to 30 marks. Similarly, if the statistics questions go in his favour, then he would expect to achieve 35 marks. But if they don't, then this reduces to 25 marks. If Jack devotes his revision time to mechanics, then he has a 70% chance of finding mechanics questions favourable and a 20% chance of finding the statistics questions favourable. If Jack devotes his revision time to statistics, then he has a 60% chance of finding the statistics questions favourable and a 60% chance of finding mechanics questions favourable. Use a decision tree to determine how Jack should devote his revision time. Okay, let's start by drawing a decision tree. So the first branches coming out of the first decision node is going to be whether he's going to revise mechanics or statistics. I'm going to use keys as I go across this just to save space. So RM revise mechanics, RS revise statistics. Now we've put on here how favourable he's going to find the mechanics questions if he revises mechanics, or how favourable or not he's going to find the statistics questions if he revises statistics. So again, I've got a key for whether he finds mechanics or statistics favourable. Remember that little tilde symbol means not. So this branch here, for example, would mean we revise statistics, but he doesn't find the statistics questions favourable. We also need to add on how favourable he finds questions in the other paper. So we also need to add on branches up here for statistics and branches down here for mechanics. Okay, so that now completes the basic 2 diagram, we now want to put on there the probabilities. So let's start by looking at this first statement here, and it says if Jack devotes his revision time to mechanics, then he has a 70% chance of finding the mechanics questions favourable and a 20% chance of finding the statistics questions favourable. That's if he devotes his time to mechanics. So that's going to be these branches up here. And so he has a 70% chance of finding mechanics favourable. So I'll put 0.7 on this branch, which means that this branch is going to be 0.3. And then he has a 20% chance of finding the statistics variable. So I'll have 0.2 on both of these branches and 0.8 here. And then we'll move on to the second sentence, which tells us about what happens if he devotes his revision time to statistics. Then he's got a 60% chance of finding the statistics questions favourable and a 60% chance of the mechanics questions being favourable. So down to these branches down here. So he's got 60% chance of finding statistics favourable. So we'll have 0.6 here and 0.4. And then also a 60% chance of finding mechanics favourable. So 0.6. 0.4, 0.6 and 0.4. Right, now we can go back to this statement up here. So Jack estimates that if the mechanics questions go in his favour, then he would expect to achieve 45 marks. And just skipping to this second bit here, if the statistics questions go in his favour, then he would expect to achieve 35 marks. Now that represents this branch up here, mechanics in his favour, statistics in his favour, and it's going to be a total of the marks. So he would get 45 from the mechanics, 35 from the statistics, giving him a total of 80 marks. Now he must be doing the AS paper because they're out of 50 marks. So basically what we've got is 80 out of 100. Now the other place where he has favourable mechanics and statistics questions is going to be here. So this place here was also going to be 80. Then we just look at the next piece. So now we're looking at mechanics in his favour, stats not in his favour, and that would be a total of 45 plus 25, not 42, 45 plus 25, so that's 70. So mechanics in his favour, stats not in his favour, 70 is going to be on this branch. And there's another place where he has statistics not in his favour, mechanics in his favour, so this one's also going to be 70 as well. So put that in. Next we're looking at not favourable in mechanics, but favourable in stats. So that's going to be 30 plus 35, so I'll write that down, 30 plus 35. So that's going to be 65. Not favourable in mechanics, favourable in stats. Where else is that? That's here. Not favourable in mechanics, favourable in stats. So this is also going to be 65 here. And then lastly, not favourable in both is going to be 35 in mechanics and 30 in mechanics and 25 in stats. So that will be 55. So not favourable in both, this branch here, and it's also this branch down here. So this is also going to be 55. So now we can start working out the EMVs. I'll maybe show the working for one or two. So the working for this one here will be 80 times by 0.2 plus 70 times by 0.8. 80 times by 0.2 plus 70 times by 0.8. And that will give me a value of 72. So let's put that in the circle. Next, for this one here, we will have 65 times by 0.2 plus 55 times by 0.8. and that gives a value of 57, so we'll put that in the circle. Next we'll have 80 times by 0.6 plus 65 times by 0.4, which is 74. And then 70 times by 0.6 plus 55 times by 0.4, which gives us a value of 64. And then working backwards, work out the EMVs here. 72 times by 0.7 plus 57 times by 0.3, which is 67.5. So that can go in here, 67.5, just about squeeze that in. And then for the bottom one, we're going to have 74 times by 0.6 plus 64 times by 0.4, and that gives a value of 70. So I'll put 70 in here. So next thing now is to look at the EMVs, and I can see that RS has the higher EMV. So what should Jack do? I think he should devote his revision times to statistics because it has a higher EMV than revising mechanics. So putting that in a sentence, Jack should devote his revision time to statistics as its EMV of 70 is higher than 67.5, the EMV of revising mechanics. Better still, he should just use Heinz Maths videos and just revise a lot. So you should now be able to do exercise 8A, and that's on pages 249 to 252 of the exercise book.